Okay, good morning everybody. I hope everyone's having a wonderful day. So I'm going to pick you up again from last day. I have a habit of saying this lately. Last day we started talking about quicksort. So I gave you this idea. I kind of drew this picture. We had some fun with our crew down here. And we had this idea where I pick some position. I call it the pivot. I called it X in my picture. And the whole idea is that I try to make it so I have two groups of elements. The elements that are less than or equal to X, and the group of elements that are greater than X, right? So I had these two groups, and the idea is that I would recursively sort those, and the whole idea is if I could sort both of those groups, I could put them back together by taking the elements in L, then I put the pivot, and then I can have all the elements that are greater than X on the right side of the pivot. If we can do this, then we can most certainly sort an array, for example, using this idea, right? So this is the core idea of quicksort. So today's lecture, I'm going to be going into much more detail about this. Last day I gave you a high-level intuition and why it worked. Now I want to go into a bit more detail of how we actually do this idea. How do we carry this out? So there's a lot of nitty-gritty details around quicksort because quicksort has been studied for a very long time. Even back then, even back in the 50s and 60s, people were thinking about all sorts of different ways of sorting arrays. And they had all sorts of interesting things they proved back then. And so these are very intense. These are problems that have been studied. I don't want to use the phrase studied to death, but it most certainly have been studied very thoroughly. So the big part of this, you'll notice that if I have these two groups, we have the idea that I could sort them once they're in these smaller groups recursively by using the same idea, this idea, right? Until they're either of length. So there's only one of my friends left or no friends left, right? So if I have just one or no friends, then they're sorted by definition. So there's this problem here. In my picture, I just drew it like this. I made a couple of presumptions, by the way. You'll notice that I kind of drew it where the X is somewhere like equally, kind of somewhere in the middle. This is an intuition I would like to have, but this is most certainly not always going to happen, as we're going to see. So depending on how I pick this pivot, it may be the case that, say, this group L is actually much, much bigger than G. It could be the case that they're roughly of equal size, like my picture here. It may look like other things. So just keep that in mind. It will come back to that later this lecture. So there's this thing, like how do I do this? So remember, the whole idea here is that I'm going to have it where I give you the array or some subarray. I'm going to have some elements here. And then I'm going to have whatever element I call the pivot, right? So I'm going to always presume that this pivot is in the last position. And the idea is that after I do whatever I need to do to accomplish turning this into this, I then have these two groups I can clearly isolate and sort separately. Does everybody understand the idea? So now what I need to do is I need to talk about how I actually make it so it looks like this. So that's the first step. And once we have that, we have all of the ingredients to talk about and actually present quicksort itself. And now you might ask, okay, so Dan, why do we care about like quicksort? What is this thing? So I should mention that the name quicksort came from the fact that at its time, because there's many sorting algorithms. By no means are the algorithms I'm showing here a complete list. There's many more out there. Some that even perform better than these ones in practice that have come along later since then. But they usually use a lot of these ideas. This is why I want to show them to you. But quicksort, for example, the reason why it was called that by its original, the person that originally developed or discovered it, is because at that time period, whether it be in like the other algorithm I'm going to show you, a lot of the ones I've shown you, is that if you implement it appropriately in practice at that time, it would perform 2 to 3 times better. So that's where the name quicksort comes from, is the original author of the quicksort algorithm. Which I'll lovingly just mention that some people also call quicksort Hoare's algorithm. I know somebody over there snickering about this. You'll see why. I guess you can see why maybe it didn't really pick up. Usually people call it quicksort. Although Tony Hoare is an impressive computer scientist, did many, many things. Many, so many that some of the things I even teach you are influenced by some of Hoare's work. But you can see why the name, like usually when we see some of our algorithms, sometimes they're actually attributed to the author of them. You can see why maybe this didn't necessarily stick over the years. Snicker. But anyways, I want to talk about how we could do this process. So there's at least a couple different ways you could do this. I'm going to be showing you one way of performing what we call this partitioning process. So we call it a partitioning process because what it does is we take the pivot and we put everything with respect to the pivot, right? We talked about this last day. So I have two different groups. They don't have any overlapping elements in them. So they form what we call a partition for those that are really into the mayonnaise or mustard. So they split them into two groups. So I need some way of doing this. Now there's a lot of ways I could do this in quadratic time. In fact, you can adopt things like your insertion sorts, bubble sorts, and so on to just simply compare it always against the pivot. And you can see if you can make something like that. But most certainly, we would like to do better than this. There's other ways of doing this so we don't need quadratic time. What I would like to do is instead try to achieve this in linear time. So the partitioning scheme I'm going to show you is called Lomuto's. So this one, if you're curious about what this partitioning scheme is called, it's called Lomuto's scheme. So if you ever find yourself going really into deep about this is Lomuto's partitioning scheme. There's also Hoare's partitioning scheme, which is the one that originally Hoare's algorithm used. So that is a different scheme. So just be aware that these two exist. They do somewhat different things, but they both achieve linear time. So I'll convince you of this later. So the algorithm goes as follows, and we're going to do an example of this. So I'm going to scan from the starting index to the end index -1. I'm going to go over this range here just before the pivot. Because remember, I'm just going to always presume the pivot's in the last position, such that when I do my last step in this process, it's going to move the pivot in between the two groups L and G. So I need to figure out these two groups. So this partition subroutine is going to do this for me. So what I'm going to do is I keep track of two indices. Namely, there's going to be one that's always going to be used to scan from left to right. There's going to be another that's going to keep track of whenever a sub j is less than or equal to x. So what's going to happen is we're going to have this index j that's going to scan from left to right. And we're going to have another one that's going to start off as -1. But every single time I run into an element that is less than or equal to the pivot, it's going to go up by 1. So whenever I run into an element where this happens, I'm going to increase this value. But here's the thing. There may be other indices that come along that are going to have it where they're bigger than the pivot. But I would like those to stay on the right side of my pivot at the end of this process, right? So the one thing I have to be careful about is I need to make sure that all the ones that are bigger than the pivot stay on the right side of all the ones that are less than or equal to the pivot. So we're going to use a swapping process whenever I have the opportunity, whenever I see that, oh yeah, look, I know this is the case, so I'm just going to swap just in case if I run into those. And here's the neat thing. Whenever this fails to happen, where a sub j is not less than or equal to x, that means I doesn't get incremented. So that means that if you never run into it, that means that whatever you stick in that spot, when I increment I, had to have been the case that whatever was sitting there is either less than or equal to the pivot, as in it's ourselves, or it's going to be an element that's bigger than the pivot. So if I swap it, I'll guarantee that everything that comes just before, because remember, a sub j was less than or equal to x whenever this happens, right? So that would increment I. So I is actually being controlled by how many times this is successfully done. So we'll see this actually when we do the example. So whenever I have this, I'm going to shove the ones that are less than or equal to the pivot onto the left side by just performing, instead of just imagining it like I'm shoving it, I'm just going to swap. So whenever I do this swapping action, this will guarantee that I'm not going to actually have any ones that are less than or equal up to this position J. So you're always going to imagine it like when we did like something like insertion sort. You know how we kind of like scanned from left to right and we partially built a sorted list or sorted array? I'm going to do the same thing, except now I'm just going to be making sure that everything less than or equal to this position, J, is always going to be less than or equal to the pivot if I happens to be whatever position it has to be where the split occurs. So as I go along, I'm going to move J, but everything up to that point has to be the case that if I only examine those elements up to J, wherever position I is, it has to be that all of those ones from position I and less are less than or equal to the pivot. So you'll notice this when we do the example. But when we're done this process, when I sweep through all the way up to the pivot, but not obviously the pivot itself, I'm going to swap whatever that position is one higher, because remember we said that whenever our given position is less than or equal to the pivot, it's controlled by I, right? So everything up to I is less than or equal to the pivot at the end of this process. So that means that at the end of this, if I go one higher for I, that means that I'm in the middle. It's not truly the middle always, but I'm between these two groups, L and G. So if I just swap whatever's there, which would be in the G group, I can guarantee that I'm going to be in the middle. You're going to see this in our example, and I'll just return this position. That's where the position of the pivot is. So knowing this position is very important in this process. So let's go through this. So one thing I should clarify is that the position of I, now let me see, did I put I in there? Oh, we have two lines I'm missing up here. Let's put those in here. So there's two more lines right here. I knew I was going to miss something here. I talked about them, but I didn't write them. So let me add them in right here. There's two lines that happened just before this. We're going to have X, because obviously we need X here. X is going to be assigned A sub n. That is just simply the pivot, right? Like in my picture. And then I'm going to have I being assigned start minus 1. So you know how I said minus 1? That would be the case if I was start with 0, right? So just keep in mind this goes in right above this for loop. But I explained it, but I didn't write them down. My apologies for that. I knew I was going to miss something. So here we go. Let's go through this example just to see how this plays out. So I like to think of it like I have a couple of fingers. You're going to see this idea of like keeping track of a couple of positions again when we see merge sort. So we're going to see a subroutine there that's going to be kind of like this, but it's a different idea. So what I want to do is I'm going to scan J. I'm going to go from all the way from left to right. Every time I run into an element that is less than or equal to the pivot, right? Remember, this is what X is. Remember, this is X. What I would like to do is I would like to increment I, and I swap it with whatever A sub J is. And you're going to find out that if we keep running to elements that are less than or equal to the pivot, it's just going to swap with itself. Nothing too interesting. So if I perform the first iteration of this loop, so I start off at start here, I notice that, yes, 2 is less than or equal to 6. So I'm going to increase I. So now I is, in fact, 0. And I swap A sub 0 with A sub 0, right? So this is going to be, so we have this range here. It's going to be the start to the end. We're going to see that these are going to get modified through this process. So the whole idea is that I'm going to have start and end indices. So we're going to only care about this subarray. So it starts off at position 0 in our example. I'm just doing it over an entire array here, just in my example here. So you'll see that my parameters here is the array A here. This is what A is. Position 0 is start. Position 7 is end. What is that in between start and end? Between A and end. A and end. Over here. Start. So we got A. Just clarify with me here which one where we're looking. Okay, well, let's keep going. And if you, x is assigned, so x is assigned a sub end. Yeah, it's a sub end, square brackets. Remember, I want this one to be the pivot because I'm going to compare everything against the pivot. Excellent. So let's keep doing this. So I'm going to now, so remember, I swap this with itself. Nothing happens. I'm going to increment j. Notice that I have 3 versus 6. 3 is, in fact, less than or equal to 6, so I'm going to increment I. But notice that every time I go through this process, as I scan through, everything that is less than or equal to the pivot is always going to be wherever I is and before, like I said earlier. So notice here that so far I am building a partially complete L group. So now I'm going to go to the next iteration. Okay, now I have 10 versus 6. We know that 10 is greater than 6. So do we increment I or do we not? We don't, right? We don't. We don't. We don't do any swapping. Definitely. So let's go to our next iteration then. So just remember that wherever I is, everything to the left of this, up to this position so far, if I examine all of these, you would have actually a partially complete grouping of L and G, just up to that one position. So now I have J. Okay, I have 1 versus 6. 1 is in fact less than or equal to 6. Do we perform the swap and increment I? Sorry, we increment I, then perform the swap. Do we do that? Yes, this time we do. Now this is what I'm talking about here. So remember, everything here and before at position I is less than or equal to the pivot. So what I would like to do is I would like to extend that by allowing me to put it in. But here's the thing. It almost looks like a bookmark where imagine I'm reading a book and I find this part I really want to be interested in. So I put that bookmark in and this is my bookmark. So I want to move it to the next page because I'm going to read another page of the book. So I'm going to increment I. So now this right here must be in the G group. So I'm going to perform the swap here. So now I'm going to swap 10 and 1. And notice that I've now extended the L group by 1 element. And this is indeed going to be greater than the pivot. So we're still doing okay, right? So now let's proceed. So I'm going to increment J again. Well, now look, 5 is less than or equal to a 6. So we're going to have to do another one of these swaps, right? So I increase I by 1 because I'm going to read another page in my book. So I'm going to perform the swap here between these two because I want to extend the L group by 1, right? So now, if I keep going, notice that I do this again. Got J here. Okay, that's 7. That's bigger than the pivot. No swap. Bigger than the pivot. No swap. Now, look at this. Look at this. Watch this. Watch this. Remember, everything less than or equal to the pivot is up to position I. So everything after that is larger than the pivot or is the pivot itself. So the pivot is a very special dedicated element here. I would remember, like my picture, I want to put X in between L and G. So I'm going to just perform this last swap between A sub end and A sub I plus 1. That's the next position right here, right? That's I plus 1 right here. So I'm going to swap these two elements. So I have 6 is going to go right here. And I'm going to put 10 right here. Because I'm just going to swap those two. This is not the pivot anymore, right? That's just, so now notice here, that is actually all I do with this partition subroutine, and I'll just return this position, I plus 1. Notice everything before the pivot is less than or equal to 6. Everything after the pivot is greater than 6. Is that fascinating? So it actually uses some of the ideas you may have seen before, it just twists it a little bit. where instead of it being, you can almost think of it like we're almost doing a pass-through, like one of our simpler sorting algorithms, except now instead we're just going to keep track of the elements whenever I run into them. I'm going to keep all of the ones less than or equal to the pivot on one side. So I don't perform the swapping process, but I keep a little bookmark to help me keep track of this. So are there any questions about this? I will stress that I gave another example actually in the notes that's just very similar to this, except I made the pivot 4 instead of 6. So I thought I would give you a couple examples you can walk through. So this is where I used a pivot, it was 6. So hopefully you found this fascinating. Are there any questions about this partition process? About how we carry it out? Or does this seem pretty clear? You're going to find very quickly that this is most of the meat and potatoes of quicksort. Okay, so if we're doing good, give me 2 thumbs up if we're doing good. Okay, excellent, excellent. So let's talk a little bit about this. So now imagine we have this process. So now we know how to do this. But here's the thing. I would like to recursively sort these 2 things and then put it all together. So what we're going to do is I'm going to talk about quicksort in a moment, but I want to first address one other detail here, is the time complexity of this. So notice here, if we go through our analysis, this is some constant number of operations. Outside also this part here, that takes a constant number of operations. A swap can always be done with just some other temporary variable if you like. So those you can do a constant number of operations, but you have a loop right here. Can somebody tell me how many iterations does this loop perform? Actually, I'll ask you how many iterations does that for loop perform? Not necessarily swaps. So it's not X, it's not X. Yeah, it's going to be involving this range here, right? The start and the end govern how many are going to occur. The easy answer to this is it's going to be at most the number of, so if I'm looking at how many swaps happen versus the number of iterations, the number of iterations happens regardless. It's going to be based on the number of elements in this range from start to end, right? But the thing is, notice here, I just look at just this, right? So notice that it involves the big O here is actually based on the number of elements, but most certainly if you take this into account over the entire length of the array, it's going to be big O of n. It's going to be linear. So the big thing I want you to take note of is that the time complexity of partition it's linear, right? It's linear in the number of elements for this range start and end. That's the big thing. It's linear, right? But it depends on this number of elements I examine. You're going to see that I could be rather generous about this. I could just treat it like it's big O of n. Sometimes it actually really matters to be a little bit more careful than this. But just keep that in mind when we actually get to the analysis of quicksort, okay? So you're going to see that regardless of whatever happens, this partition is going to take linear time. This is because, notice this for loop is going to happen regardless. And that's what's going to attribute to the time complexity here for partition. So let's head over here. Let's talk about quicksort. Now that I've shown you actually the toughest part about quicksort, and this is one thing that helps me about when it comes to quicksort, delineating it from other sorting algorithms, is quicksort not only does in practice does it work quite well compared to many other sorting algorithms, it's also rather easy to implement. So I like to also think of it like quicksort. It's quick because it's simple, it's fast. I'm not claiming it's the fastest, that's a whole other remark, and there's other concerns around that. But it is most certainly easy to implement. So notice that algorithm I gave you for partition's fairly straightforward, right? It's all a bunch of just swapping and array indexing, right? So you can see very quickly, like, oh yeah, that's not that hard to make that in C++, right? In fact, I encourage you to do it. Now I'm going to show you how I could just write a quicksort. You're going to see very quickly that also this is very easy and natural to implement too. Like there's not very much complicated stuff going on. Remember, we talked about different appealing features of algorithms? Quicksort is extremely easy to implement. That is one nice feature about quicksort. So if you're looking for like an algorithm to pick up very quickly that tends to work pretty good, quicksort is a nice ideal candidate. In fact, many libraries, when use sorting, very often it uses some flavor of quicksort. Not all of them, but some of them. It was quite common back in the day to do so. I can't recall if the standard library still does. I think it does still. I can't recall. But anyways, I wrote it explicitly in terms of two different algorithms. One's the driver function. You know how I talked about that the other day? The other is the recursive algorithm. So I have quicksort here. It calls QS, which does all of the work. The initial parameters for this are going to be a start index and an end index. So the start index is going to be 0, end index is n minus 1, because I'm going to have an array of length n. It's going to have n comparable objects. So most of the meat and potatoes is actually right here. So there's a couple things I want to point out. First, look how simple this is. I mean, this is, ignoring partition over there, would I be able to convince you that this is actually a little bit, like if you were to just say, okay, how would I implement this? That's just a function call right there, and these are two recursive calls. You can literally just write this out, and it's actually not that much different from this, really, at all. In fact, you would argue that maybe, just maybe, I might be able to sway you on the idea that this may be simpler to implement than some of those big O of n squared algorithms that you've seen before. At least if you look at this and you're like, okay, that's all it does? Like, just wow. So, anyways, I'm going to have start and end. These are going to be start and end indices. They're going to serve a very similar purpose to what I had over here. Now, the whole idea here is I'm going to apply this sorting on the range of start to end. So this call right here, once this completes, it's going to sort A given positions start and end. So that subarray is going to get sorted by this call. So naturally, if you make it 0 and n minus 1, you're going to sort the entire array. That's why those are the initial parameters for QS. So here you go. You have an if statement. This is actually, you'll notice that I'm implicitly discarding the base case. Does everybody see that? So notice there isn't like a base case that I've explicitly written out. We don't send the length of the array? Well, yeah, it's right here. It's right there, right? N minus 1. That's the initial call. So there's going to be an initial call, the driver function, that's going to call this recursive algorithm right here. So its initial parameters are position 0 to, and then the end is going to be n minus 1. So notice that if it is the case that start is bigger than or equal to end, that means that the intervals are in fact are going to cross. This should remind you a lot of binary search, right? It's actually, I wrote it like this so it looks a lot like binary search, that way I showed you it the other day. So I did that deliberately. So notice that if you had it the other way around, that would guarantee you at least one element, right? But not just one element. In fact, it's actually technically at most two. Because if start and end aren't the same, that means that there's two distinct positions. A start position, end position. That means there's two elements. That's why we're going to apply this recursive case. So if this is satisfied, there's two or possibly more elements to examine. Otherwise, you're dealing with 1 or 0, which we know by definition those are all sorted. So the first thing you're going to do is, now I've added this in red. I'm going to read this very carefully because I know that red is not the easiest thing to read, especially on a whiteboard like this, is that this is actually an optional step. It's actually something you can easily modify this algorithm to do. And this is something I'll talk more about in a moment, is that you can select a position called pivot and you swap a sub pivot with a sub end. So I talked about this actually the other day. Do you remember me talking about the idea that you pick this pivot? It's a special position that you can compute. And the idea is that if you want to use our version of quicksort that uses this Lumuto partitioning process, what you do is you swap whatever the pivot is into the last position. So this is that step right here. So if you plan to only use the last position always, you don't need to perform this step in red. However, if you want to pick, say, the first position always as the pivot, or the middle position as the pivot, or the median as the pivot, or you want to pick a randomized pivot, this step is what I'm talking about here. So you just do this every single time, and remember that quicksort works regardless of how you pick this pivot. Remember, the whole idea is it splits it into those two groupings every time and it recursively sorts them. So this depends on what we call a pivoting strategy. I'm going to talk about that shortly. So the pivoting strategy might actually affect the time complexity of quicksort. So I'll first start off by ignoring this step, and then I'm going to start talking a little bit more about, okay, what can we do to buff up quicksort? So for those that aren't aware of that phrase, I'm just saying we're going to see if we can make quicksort faster. So then you call partition in here. So if you have two or more elements, you're going to call partition. It returns a position. P, that's the pivot. Then what you're going to do, so this is the position of the pivot like in my example right here. So like this one right here, it gives you the position of 6 in our example. Then what you do is something that should remind you a little bit about binary search. Does everybody remember that I computed this guess like mid, and then I discarded whatever I didn't need to examine anymore, right? But I didn't have to consider my guess because I check it against the key, right? I do the same exact thing here, except I'm going to apply two recursive calls. One on the left half, one on the right half, regardless. Because remember, we're not searching, we're sorting. So the whole idea here is that if I know the position of the pivot, so it's at index P, the L group is actually everything to the left of position P. The G group is everything to the right of P. So those are going to be our two corresponding recursive calls, like in my picture I drew at the beginning of the lecture. So there's our two recursive calls right there. And that's quicksort. That's all I have to say about the algorithm itself. So are there any questions about this algorithm as I've written it here? Is that kind of nice? So the recursion really makes this very natural to express. How do we collect the sorted elements? Now this is the catch. This is really neat. Now remember how I told you the other day that I'm always going to presume that whenever I pass parameters, especially like arrays, specifically arrays and anything that isn't a primitive type, I always pass it by pointer. So the big thing I want you to notice is when I do this process, it's like, for example, when I did partition over here, when I pass it to these recursive calls, I'm actually working with this array that I perform partition on. So I don't actually create multiple copies of arrays. They're all just one array. So this is actually really a nice feature of quicksort. But remember, it still uses recursion, which means that it's still going to perform these recursive calls. It's just now I'm going to be carrying around a pointer to an array, as opposed to making copies of arrays. So when it comes to collecting up the elements, remember, my picture is very simple. It's very simple. Remember, when we put them together, here's the fun part about this. I don't have to do anything. That's the fun part of this. The recursion's doing it all for me because I've already organized the array. So there's the big surprise for you, is that you know how I talked about putting it together? That was just the conceptual idea. Notice that I already have the pivot right here, right? I have my L group and G group. If I can sort this and I can sort that, the pivot is in the correct spot. So I have actually technically done this implicitly. I've implicitly put it together by knowing and of actually organizing, using this partitioning scheme over here, I've actually arranged it so that it's L, then the pivot, then G. Does everybody see that? So I don't have to do anything more at this stage. So if you're, say, for example, you adapting, say, a more complex data structure, you may explicitly do this whole combination process. But when you're doing this over an array, since all the elements are contiguous like this, you don't have to do any more work. I've actually organized it already so that I could just simply just know where L is, where G is, and they're already in the correct spots. Yes, exactly. So pointing out, oh, so the pivot changes in every recursive call and everything gets sorted. Correct. So every time I make a recursive call, it's going to select a pivot. So I'm going to select this pivot again, or if I just assume it's the last position, it's the last position. And remember, these are just two recursive calls, so they're going to be applied over this range. So it's going to apply QS again. And notice that it's going to go through this whole pivot process where it finds the position, then it recursively applies this. Just like my example, remember I drew that picture on the board where I had it where it was breaking into the smaller and smaller pieces. The idea is that I stop performing these recursive calls when I only have one element or no more elements in a subarray. And that's when these start and ends, they cross over each other. But yeah, that's actually a really great observation. I appreciate somebody brought this up, is that every single time you're going to go through, when I call this, it's going to be calling this all over again, using these as start and that as end, and so on. But yeah, it will select, like if you have a different way of selecting the pivot, it will select a different pivot, but only over that range. And that's why you'll notice I wrote it as sort A from A sub start to A sub end. So everything is related now to start and end. That's why we need this driver function to set up the start and the end of the entire array. It's a wonderful observation. Now anytime. So I want to talk about analyzing quicksort. So there's a couple of things I want to point out to you. The first thing is notice that there is this selection of the pivot possibly. But I'm going to first focus on whenever we pick the last element as the pivot. I'm going to start off with that. I'll make some remarks about this pivoting strategy, like how you pick the pivot in a moment. But take notice that I make two recursive calls. Now, remember when I drew my picture, right? Like even this picture here, it's somewhat misleading, right? Because P looks like it's about the middle where these are about roughly equal size, right? We found, for example, when we dealt with something like binary search, it seemed like a very natural thing to happen where we have it in the middle, and then we have things that are roughly equal size. We found out we got something that looks kind of like logarithmic whenever I discarded about half of them each time. The inverse of exponential growth, it's like I always discard a half every single time. So I would like to do something kind of like that, where I half things, but the thing is, I'm still considering the entire range here. So the first thing I want to point out to you is that regardless of whatever call I'm in, whenever I call partition, it takes linear in the number of elements in that range, right? So the natural question is, what happens when we take up our analysis techniques we've figured out so far and we apply it here? So first, if I ignore the recursion, notice that if I were to do this, say for example, I just ignore this red part here. If I ignore that, I know partition takes time that is linear based on start and end. Then it does these two calls, but I'm just going to ignore the recursion. I'll just assume it's some constant number of operations, just for the sake of our discussion here. If I do that, in the recursive case, notice that this will take time that is linear, right? If it's the base case, I'll just evaluate this and say, oh, okay, nothing happens, so I'm just going to stop. So it's some constant number of operations in the base case, right? So we're going to make very few assumptions beyond that about the pivoting strategy, but I'll talk more about it later. But I'm just going to pick up a few things. The first thing I want to bring up is that, technically speaking, I want to start off with the best case analysis because it'll actually match the intuition I had every time I drew that picture. So we're going to see this in a moment. So I have two recursive calls that happen, right? But each time it performs something that's like linear amount of operations, right? Something like big O of n, if I want to be very generous. I don't have to be, but I can if I'd like in this analysis. So I want to first focus on the best case analysis. Then we'll work our way. We'll go best, average, then worst. How's that sound, everybody? That sound pretty exciting? Give me a thumbs up if that sounds exciting. So maybe we'll start a little optimistic at first, because I've been bragging about this quicksort algorithm all class, so maybe that's a good place for me to start. Well, we'll be optimistic this Tuesday. So let's start off with the best case analysis. So the best case scenario is going to be where L and G are roughly equal in their size. Using the intuition that we had from binary search, the idea is going to be that we would like to make those L and G shrink as fast as possible. So every single time, if I make them roughly the same size, if I do that, notice that I'm always going to be halving the number of elements roughly every time I make one of these calls to QS. Does everybody see that? So every time I do partition, what will happen is X will get placed roughly in the middle. And then what happens is I have one call on the left half and one on the right half. So it cleaves roughly in the middle, means that it's going to take and dissect it in two halves. So if I do that to each side, it'll make them so it cuts them down a little faster each time. In fact, this is probably the fastest way you're going to be able to do this. We're going to see that how fast we can cleave the array into chunks down to where they're sizes of 1 and 0. If the fastest we can do that, that will yield the best case. The worst case is going to be where I try to make it so that this partitioning process is very unsuccessful, and it makes that so that the partitioning process puts X in a place such that every time I make this recursive call to QS, it's always going to be dealing with something that is pretty big. So it's not going to be like my pictures I've been drawing up to this point. So the best case scenario is when there are n distinct elements where the pivot is so that the number of elements in L and G are roughly equal. So for those that are curious, actually, I'll ask you about this. So if I want to pick a pivot, so imagine I have my some set of elements in an array or even a subarray, and I would like it so that X is somewhere about the middle where these are two roughly of equal size. What would X need to be to make that happen? So think in terms of, imagine this is a list of numbers, and I would like to make X so that it's somewhere about the middle. So for those especially that have maybe seen a little bit of statistics, you may have a good idea. Because remember, imagine this like if it was going to be sorted. Because remember, imagine X is going to be in the middle, then I would sort L, and I sort G. So you know when this is done, X is going to be whatever would be in the middle of that sorted list. So we have actually a name for that. There's a name for that. What would X be if I gave you a set of data like this? So think of it just as an array of numbers. What would we call that? I know that there has to be somebody out there that studied a little bit of statistics. I know you have. There's got to be somebody out there. There's a term for this. It starts with an M. It's the median, yes. So if you can make it so it picks the median every single time in your instance, it will always be that it always picks it so it looks like this. Very good, very good. So in these cases, so I'll say this happens when X is the median. So if you can make sure that that pivot is the median, for example, you're in good luck. Well, you're in good happy days, because it will look like this best case scenario. So instead of walking you through doing iterative or repeated substitution, I thought I would draw you a picture to give you an intuition for how you would compute the time complexity. This is actually based on a technique that I usually show in 340 called the recursion tree method. So what I'm going to do is I'm going to start off with determining the amount of operations that happen say, in one call of QS after each successive call. So we know when we start off, we're going to perform that partition process, right? But notice that all of the time complexity of this is some constant plus the number of, like something like big O of the number of elements that I have to examine. It seems like the number of elements I need to examine in that range start end seem to govern the time complexity of this. So just for the sake of charity, because I start off quicksort with n elements, because I start with 0 and I go up to n minus 1, that means there's n elements, right? So if I do my initial call to partition, we know this takes big O of n time, right? So imagine this as the initial call for quicksort. So what I'm going to do is I'm going to keep track of the total amount of time that takes place over the entire execution of the algorithm. I'm going to tally that here on the right-hand side. I'm going to draw out a call tree akin to the one that I drew out, say, for example, our Fibonacci example, except I'm going to write out how much non-recursive work happens in that given call in relation to the number of elements that it examines. So I'm not going to worry about those constants because they're not going to make much of a difference here. It's really just that partition process seems to govern this. So in this call, I perform two recursive calls, right? In the best case, L and G are going to be roughly equal in their size. So it's going to be approximately n over 2. Approximately n over 2. It's not going to be exactly this necessarily because, remember, I discard whatever be where the pivot is, right? But this will serve as a nice upper bound on that. But look, when I do partition here, it's something like big O of n over 2, or just you can think of it as n over 2 plus or multiply some constants. And the same thing here. Regardless, if I sum over the amount of work that happens amongst these two calls, it's still going to be big O of n. Does everybody see that? So if I count up all the operations that happen in these first two calls, it's still going to be big O of n because there's half as many elements. But when I put these together, that's like my initial call, right? But remember, each one of these might perform two recursive calls. So if they're approximately n over 2, and I perform two recursive calls, roughly how many elements are in that range from start to end for these calls? Roughly how many? Well, I'm not asking over all the total, but what would I put in this box here? N over 4, yeah. But you're getting to the right point. You're getting to the right point here. So these are all going to be approximately a quarter of n. So n over 4. Approximately n over 4. I can go through the same exercise and count up all the operations that happen on all these recursive calls. It's still going to be big O of n. But remember, notice that every single time I do this, it goes down by a power of 2. Does everybody see that? Notice it's n, then it goes n over 2, n over 4. You'd see that the next one's going to be n over 8, then n over 16, then n over 32, and so on. But you should notice and remember from our previous lectures, we had something kind of like this. Not necessarily the same way, but the same mathematical phenomenon happened. Every single time I made a call, it goes down in its size by a power of 2. So what should you expect to happen if I were to ask you how many calls could happen? How many levels of these calls can happen? So notice the next level will have n over 4. It'll be n over 16, n over 32, until it eventually hits where there's either no elements or one element. So you can tell me in big O terms. So how, like if I were imagining this like one pathway down this diagram, you should expect it to be like log 2 of n, right? Log base 2 of n. So just like when we looked at binary search, right? Because the intuition is very simple. When I made one recursive call, every time I half it, right? My apologies, everybody. So every time I half it, I'm just dying by this excitement, by the way. So notice if I ignore all of this, it's just like the analysis we had for binary search, right? Every time it's just like when I discard the elements. Is that neat? So this is actually one way you can derive this. I'll have in the notes another way to derive it. But here's the thing. How many times am I adding big O of n? Can somebody tell me? What should I expect for the time complexity then? So what should I expect? N log n, right? Notice that there's big O of log n many times. These are happening. The depth of my recursive calls, just like, remember this is like, think of it like a call tree, like my Fibonacci example the other day. I'm just counting up how much work happens. And this keeps going down, right? But it happens in relation to big O of log n. If I multiply these two things, the n's by log base 2 of n, I end up with big O of n log n. So this is actually the best case time complexity. So notice that this is better than big O of n squared. So notice that this is similar to the analysis we had for binary search if you just ignore everything I do to the right of this. Did everybody see that? So really what governs this is how long one of these paths can get. So that's going to be what governs how tall this diagram would be. And all I'm doing is counting up how much work happens. But the neat property here is that every time I'm splitting it across, I'm equally spreading it across, right? That's why every time it's linear time in total if I add them. Is that fascinating? So the best case behavior of this algorithm is when x is something like the median, the pivot. So you're going to notice that in some pivoting strategies, if you can compute the median efficiently, you can guarantee this running time. Can everybody see that? So if you can tell me a way to compute the median, so what position the median has, you can actually modify quicksort to run in big O of n log n time in the worst case. Just the question is how you do that in big O of n time, because the total amount of time you have is linear time for one call. So I won't be focusing so much on how exactly you do that, but it does exist. So I'll make some remarks about that in a little bit. The next thing I want to point out is that in the average case, you also get big O of n log n. So this is also true in the average case. For those that are interested in statistics, what you just expect to happen, statistically speaking, is that it will average out where the pivot would be somewhere in the middle. Just like in the analysis for binary search, you would expect that the guess where the key would be somewhere in the middle. It uses a very similar statistical argument. Just the thing is, here you would consider all instances where the pivot is the first position, consider all instances where the pivot is in the second position, third position, fourth position, all the way up to the last position. So you would imagine that you pick each one of these as a pivot in those cases, and you would see, okay, when I calculate out how many operations happen in each one of those cases, it averages out to something that's like this. So that's some good news for you, because up to this point, if you're thinking about bubble sort, selection sort, insertion sort, none of them have average case time complexity of n log n. Is that interesting? So we got something a little better now. So now this brings me to the worst case. That's all the good news I have for you so far. Let's start off with the bad news now. Is that you might say, Dan, that's lovely. Like that means that we can actually get past that big O of n squared, right? Well, I got some bad news for you. No, it doesn't. It doesn't get rid of that issue. But, like I said, there are ways to achieve that running time if you're clever about how you pick the pivot. But I'm just going to assume the most pessimistic selection of the pivot. And in fact, picking the last element of the entire range is sufficient to actually get the worst case to happen. It actually occurs when the array is already sorted, if you actually pick the pivot to be the last spot. So let's talk about the worst case. So, worst case. Suppose the last element is the pivot. So suppose that I go through this partitioning process and I find out that that last spot, that the very last spot, ends up being where the pivot goes. So it's like right off the furthest right. So if we are sorting n elements, just for the sake of discussion, n elements, L consists, so our less than or equal group consists of n minus 1 elements, and G has none. None. Zitch. Nothing. It has nothing. So in this case, what it will look like is something like the following. So imagine you have an array with n elements. So the pivot goes right here at the end. That means that there's n minus 1 elements. So this would be L. G has nothing. There's no elements in G. So when you make the call, the second recursive call, what will happen is it will just simply be the base case and it'll just stop. So it doesn't do anything beyond that. So this is what happens. So watch this. So every time I pick it as the last position, you get something like this happening, where you always go down by 1 element. So on my pivot in the last spot, it always goes down by 1 element every single time. So if I'm considering n minus 1 elements, I'm going to have n minus 2 elements in the L group. So the question, by using the very similar kind of setup I used just previously, we know that doing this call here takes big O of n time, right? This one right here, well, it's still big O of n, but it's something like big O, like if you were to suppress that work in there, it would be something like n minus 1, right? Then this would be like, if I do the next one, it'd be like something like n minus 2, n minus 3, n minus 4, all the way down. The point is that eventually you'll get down to this where you have the pivot, then you have 1 element here. And then you will just have 1 element left, but that's just going to do nothing, right? But notice every single time here it does work that is linear in the number of elements it examines until we get down to the base case. So, question. So if I'm performing this n, so notice that this happens n times, right? Notice I go n minus 1, n minus 2. It goes all the way down until this is 1, right? So if you look at this, you say, okay, well, how many elements are in each one of these? Okay, well, it's 1, 2, 3, 4, 5, 6, 7, all the way up to n, right? And we know if we were to sum up that, should I end up with a linear term or a quadratic term? So something that looks linear or something that looks quadratic? Quadratic, right? Because I just described to you the arithmetic series, right? Another way you can argue this is that each one of these does work that's linear for its partition call based on the number of elements. But I do this n times, so you know it's going to be big O of n squared, right? So that means that the worst case time complexity is big O of n squared. So for more details about this, I give a little bit more in the notes, but notice that the whole idea here is the same one I talked about earlier. Every time I just decrement the number of elements by 1, and notice that I have to go through all n of them by the end of this process. So I've dragged out this process of partitioning as long as possible. This is in contrast to the best case where I try to make it so that they cleaves it in halves so it gets smaller and smaller and smaller faster. In fact, the fastest it can. So that brings me to a couple of points I want to talk about with the pivoting strategy. So you might look at this and say, Dan, this takes big O of n squared. Like, why should I use this instead of like insertion sort or something like that? That's big O of n squared, right? Well, remember, the average case is big O of n log n. And that's even in circumstances where you imagine you pick any one pivot. So keep in mind that quicksort, even though it has really nasty instances that can look like this, that cause quadratic running times, you should expect it to run in big O of n log n, which is better than quadratic. And this is something that experimentally you can also observe. It actually behaves this way. So unless you run into these, what I would call like the instances that cause this kind of behavior, you're not going to run into these always. Just be mindful of their existence. So for example, if I make it so that this is already all sorted such that the pivot's always the largest element at my initial call, you'll get this behavior. And you don't want that usually. So there's some easy ways to deter this behavior. For example, if you want to avoid this, you could, for example, pick the pivot so it's always the middle element. So you would figure out what the middle position, but I'm not talking about the median. I'm just saying literally computing the middle spot. So just like in binary search where you make a guess where you pick it in the middle, same idea. So it's very common in quicksort where they actually picked it where that step where I told you to select the pivot, they would make it so it's in the middle. So it's like roughly in the middle. So something like start n divided by 2. So that's one other way you can get around this one situation. You get something that actually behaves much more like this over here on the left board in that instance. But the thing is, you have to be a bit careful, right? Because not every instance looks like a sorted array, right? Why would you ever use another option when the median option is always faster? Well, it brings me to another point. So the first thing is that there does actually exist a big O of n algorithm for selecting the median. So that does actually exist. It is a lot more sophisticated though. It does actually require a little bit more work to implement. So I'll talk about that in one moment, but also I want to motivate something else. So just to give you a little bit of a heads up. So remember, you'll expect on average this thing to run in big O of n log n. So in practice, if you just even used the algorithm I gave you, or you do what I'm going to suggest here, you'll expect it on average to run n log n. So watch this. So here's a suggestion I can make about selecting the pivot. So let's talk about pivoting strategies. So I want to address that because that's an important question. Because Dan, if there's a way you can pick the median, why don't you pick the median? Well, yes, of course you can. So the way I presented quicksort to you is more like a framework almost. So there's like kind of like this arbitrary notion of quicksort where it runs in the worst case big O of n squared, but there's more specialized versions of quicksort. Like I said, it's been studied for many years. So let's talk about this because there are ways to make it behave like it does in the best case or average case. So the first thing I want to tell you is that selecting a randomized pivot is effective. So that's the first thing I need to tell you. So I'm coming back to the good news, everybody. So I'm going to tell you some really good news. So there's a lot of things you could pick as the pivot. So for example, so the pivot, of course, could be the last element. It could be the first element. It could be the middle element. It could be the median. But there's another option that also exists. picking a randomized pivot. So what you would do is you would take advantage of some randomization. So you would use, say for example, a pseudo-random generator or a random number generator, what we call a random number generator. And what you do is you would pick the pivot. So remember in quicksort where I had that red line, where I had, oh, you pick the pivot and you swap with the last position. What you could do, and this works quite well in practice, is you just simply pick a randomized pivot. So you just pick a random spot in that range, you swap that into the last spot, and then you just carry forward. Here's something neat that comes out of this. And it's based on the very similar statistics that give you actually the average case analysis. Is that this actually gives expected running time. So I must warn you, when I add a word like this, expected, it's because this algorithm, when I introduce randomization into it, the algorithm may actually behave differently different times you run it. Which is something that we have not seen up to this point, right? I haven't told you, oh yeah, when you run it like this time, it does this. But when I run it another time, even though it's the same description of the algorithm, it might generate a different number, which may cause its behavior to change. So this is why I'm going to add this word expected. So for those that aren't really thinking about things statistically, think of it just like when I talk about in the average case, where you should expect it to behave this way, but it's even better than that. It's expected because it's randomized. The randomization is sort of the analogous thing to the average case, but they're not the same thing. We're going to be looking at the worst case, what you should expect from the worst case. So this is going to be, that's going to have expected running time, big O of n log n, in the worst case. So it seems like if ever you were playing a game, say a very hypothetical game, and somebody was playing a game with you, and they said, hey, look, how can I pick the pivot, given this instance? How can I outsmart the person that's going to break it into the two groups? Well, one thing statistically speaking that you could find out is that picking a randomized pivot is a good strategy for doing this. So if you do pick a randomized pivot, you should expect, in the worst case, big O of n log n. But remember, this isn't a true big O of n log n running time in the worst case because it's randomized. The selection of the pivot can still lead you to things that look like that over there, but you shouldn't expect it to happen very often. It's actually very rare. So this is actually one of the things I wanted to really address to address your question, is that computing a randomized pivot is very cheap. It's very cheap. Obviously, it depends on your computer, but most certainly it's much cheaper than the alternative that I'm going to suggest. So usually you want to avoid picking the first or last, so that's another tip I want to give you. The first or last if the array is already sorted. Because if you pick the first element in an already sorted array, it'll just be the mirror version of the instance I gave you over there. So usually a way you can improve upon this is by picking the middle. But that does not give you the n log n. To be very clear, it just only gives you an n log n-like behavior when it's already sorted. So just be clear about that. So picking the middle resolves this case. So that's one thing I wanted to point out to you. One last thing is that there also is the fact that you can technically pick the median. I don't usually like talking about it so much in here. I usually talk about this more in 340. But so there exists big O of n time algorithms to compute the median. So usually it's associated with something called the median of medians algorithm. It has a much more fancy acronym that I usually can't remember that well off the top of my head. Usually I talk a little bit more about this in 340, but most certainly you can achieve in the worst case big O of n log n, like the most truest sense. Just the thing is, this algorithm, the one that I'm referring to, it has a randomized version that performs much quicker in practice, which is it'll give you something that's kind of like this up here. But there's also a deterministic version that doesn't use any randomization that is able to achieve that bound that guarantees you n log n. But remember how I talked about earlier on in the course about this idea that, oh yeah, well, what if the constants that get suppressed by the big O are rather big? This is actually one of the examples where this happens. So some people, though I don't want to say I agree or disagree, because most certainly my goal here is just to show you ideas. I don't want to give you anything to believe or not believe. Some people would use that as an argument against using this pure deterministic version of n log n, because there's actually simpler deterministic running time algorithms that run in true big O of n log n. We'll see actually one of those next class. So I'm looking at the time here. I have a question. Would you mind if you gave me 2 minutes? Could I set up the merge subroutine for our next algorithm? But I'll talk more about merge sort itself next class. Because I found we were getting into a lot of very interesting things here. And I wanted to make sure at least you see a little bit about this before you say you want to read ahead or we want to talk about it tomorrow. Because I wanted to make sure you had a little bit about merge sort. Okay, I'm just going to quickly give you the idea for how the merge subroutine works, so that when we come back to this tomorrow, well, I guess it is tomorrow, yeah. When we come back to this tomorrow, we'll go into more detail about it. So for those that want to get really on the second part of problem number 3, you have an idea for how we can go about this. And it's actually surprisingly simple. So just like quicksort, there was this one problem that we sort of try to deal with, that partitioning scheme. Like, how do we make it so it looks like the pivots between the L group and G group? What if I can give you a sorting algorithm that looks and behaves kind of like where we kind of split it roughly around the middle? Kind of like in our best case analysis, you know how we got the n log n? We found it where we had the pivot and we had our L group and our G group, and we wanted to make them smaller and smaller, but we wanted to do it as fast as possible by halving them, right? So what if I can give you an algorithm that actually just straight up cleaves the entire array into 2 pieces, so that we can get this n log n-like behavior? This is going to be the heart of merge sort. But there's one underlying sub-problem to this, is actually if I give you two sorted subarrays, how can I combine those into actually one bigger array? So just give you an example of this, and I'll give you the idea for this, then we'll stop here and we'll come back to this next class. So imagine I give you an array. 5, 7, 11. And suppose that I have n1 many elements in this first half and n2 elements in the second half. What I would like to do is I would like to make it so that this entire array is sorted. But notice that all the elements in this first half are already sorted. So notice that this is sorted, but all of these elements in this subarray are also sorted. I would like some way to combine these 2 subarrays so it's one longer array of that length. So let me give you a quick idea of how this merge process carries out. So I'll talk more about this merge process at the beginning of next class, but here's the idea, or at least here's one way I could do this very quickly. Is I create 2 new arrays. I put the first half in one of the arrays where I'm going to include a sentinel value. This is a value there to make it easier for me to implement this, such that I don't have to worry about it going off the end of the array. And you're going to see I'm going to keep track of 2 fingers that work like this. So I'm going to have 4, 5, 7, and 11. And I'll have 2 fingers. I have an I and a J. And the idea is that all I have to do to make my array sorted, let's see, I have 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. notice all I have to do, because these two arrays, it's like these two subarrays are already sorted, right? So all I have to do is actually compare the beginnings of their two parts, right? And I can work my way scanning from left to right. But the thing is, I want to see which of these two is the smallest. Whichever is the smallest of the two, I write over there. So 1 verse 4, 1 goes here. So I'm going to have 2 fingers. 2 versus 4, I put 2 here. 3 versus 4, I can put 3 here. Okay, 4 versus 10, I put 4 right here. Oh wait, I don't need to change that one. I need to change this one. 5 versus 10, 5 goes right here. 7 versus 10, 7 goes right here. 10 versus 11, 10 goes right here because 10 is smaller than 11. And 11 versus infinity. Infinity versus 11, 11 smaller. So what you can do actually, when you have already 2 sorted subarrays, is you can combine them what we call merge. So this is what we're going to talk about next day, but I thought I would walk you through this process of this merge process. So the cool part about this is you create 2 of these new subarrays. So these are 2 arrays you actually make. And all you do is you overwrite what's in the original array with this every time you're playing a game of which one is the smaller, and whenever you get the winner, you pass along the next one like they're waiting in line. So that being said, I want to apologize for taking your time. When we come back, we'll talk more about this merge process a little quicker, and then we'll talk about merge sort. So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.